This is the Study Spot Finder. We are Group 12. My name is Maria Inez.
I'm Perla del Castillo.
I'm Andrew Kwong.
I'm Darwin Mutaro.
In this final presentation, we will be covering introduction, motivation, specification, standards and constraints, block diagram, hardware design, software and hardware integration, mobile application, challenges, and administrative.
Study Spot Finder is a device that helps students find available study spots on campus using an online reservation system through a mobile application.
Our main motivation was to solve a common issue among students on campus. Many students waste valuable study time trying to locate available spots. This device will solve this problem by encouraging organization within the campus, improving the current reservation system, reducing wasted time, finding available study spots, and finally improving students' experience.
This table demonstrates our main system specifications. We have designed the device to fit these specifications, and our final product has met or exceeded them. For this project, we had to consider constraints and standards. The following were the most relevant constraints: time, economic, manufacturability, and power. And for standards, battery, PCB, and wireless.
The following diagram shows the overall interaction between the hardware and the mobile application. Additionally, it demonstrates each member's responsibilities in this project.
We are continuing now with the hardware design. For the casing, we decided to use a cylindrical design. Some adjustments were made to the original material and manufacturing process of the device. We used PVC plastic and polypropylene tubing instead of ABS plastic material. Also, 3D printing process was restricted. Thus, we hand-made the casing of the device. The casing is divided into 3 sections, which houses different components, as shown in the image on the right.
During our Wi-Fi module selection process, we researched 3 main options: CC3200 from Texas Instruments, ESP8266, and ESP12 by Espressif. Based on the characteristics shown on the decision matrix table, we decided to move forward with the ESP8266. 3 main factors in selecting this Wi-Fi module were compatibility, simplicity, and power consumption. The ESP Wi-Fi module is compatible with our database due to the large amount of community support and libraries. These make it easy to send and receive data with ease while keeping our power consumption as low as possible.
The ESP8266 is a small, low-cost system-on-chip that contains an internal 2.4 GHz antenna, which gives it superior range and bandwidth compared to Bluetooth connectivity. The method of communication used for this device is UART serial communication through 2 pins on the ESP module. Pin 1 is connected to ground. Pin 2 and 3 are GPIO pins that remain unused. However, when the device is being flashed, pin 3 is grounded. Pin 4 and 5 are used for serial communication to the microcontroller. Pins 6 and 8 are connected to the 3.3 volts during operation, and pin 7 is a reset pin that is used for debugging purposes.
For our microcontroller research, we compared 5 kinds of chips to our 7 main characteristics. We initially decided on using the MSP430 chip since it consumes the least amount of power and had a large amount of GPIO pins and flash memory. However, after conducting further research, we found that there was little support on integrating the MSP430 and the ESP8266 Wi-Fi module. And so we decided to go with the second option, the Atmega 32AP microcontroller. This microcontroller was compatible with the Arduino IDE, which contained libraries, that supported communication to the ESP8266 Wi-Fi module. Moreover, the programming language for Arduino IDE was more familiar with our team's knowledge set. Ultimately, this change did not affect the total cost, and a high number of GPIO pins was not required for this project. So the Atmega 32AP chip fulfilled all our requirements.
The Atmega 328P microcontroller was run at 5 volts to take advantage of its 16 MHz processing capabilities using a crystal oscillator. As shown on the image on the right, pin 1 is used as a reset switch that is kept at VCC with a pull-up resistor. Pins 4 and 5 are used for UART serial communication with the ESP8266. Pin 6 is used for confirmation using a push button. Pins 7 and 20 are used for power supply input voltage, while pins 8, 22, and 21 are used for ground. Pins 9 and 10 are used for the 16 MHz crystal oscillator required for the microcontroller. Pins 11, 12, 15, and 16 are PWM signal pins that are essential for controlling voltages going to the RGB LED PCBs. Pins 13, 14, 17, and 18 are used to read the input verification code through the keypad. Pins 23 through 28 are unused analog pins that we could implement in future for sensors. In order to send multiple values of information at once, a data packet was created for both the Atmega chip and the ESP module. A header and footer were added in order to be able to properly decode the packet and organize the information correctly. The key code integer was more than 1 byte, so in order to send the value through UART communication, it was sent using the high byte and low byte command in the Arduino IDE. Once received, the high byte was shifted by 8, and an OR operation was performed with a low byte to obtain the full key code.
For the supply voltage, we decided to move to a 9-volt lithium battery in order to cover the dropout voltage for our regulators, to provide a high enough voltage to supply the devices, and for its large 1200 milliamps hour capacity. To provide the adequate and stable voltage for our microcontroller and Wi-Fi module, we decided 2 fixed voltage regulators for 5 volts and 3.3 volts. Decoupling capacitors were also included to stabilize the supply voltage leaving the regulators and to reduce noise coming in from unused pins. We also performed logic conversion due to the voltage requirement of the ESP8266 for serial communication. Instead of using a voltage regulator, we used a diode resistor configuration shown on the screen that allows the logic level of the Arduino to safely communicate with the ESP module. For the LED research, we wanted to recreate an effect similar to that of the Alexa LED ring. However, most of the components we encountered required too much power to operate and were too expensive to keep our device in budget. Since it is supposed to be produced in mass quantities, we ended up setting on the RGB LED because of its low operating voltage, low cost, and accessibility. For our PCB design, we chose to create 2 separate PCBs. Our main PCB houses the essential components, including the microcontroller and the Wi-Fi module. It contains the voltage regulation along with a connection to the 9-volt lithium battery. It also contains connections to external components as well as the 2 LED PCBs. Our final decision was to use two single RGB LED for better placement, size, cost, and power consumption. This LED has its own PCB for mobility of location within the device, and it requires a maximum current of 20 milliamps. The RGB LED has 3 pins for red, green, and blue, but only red and green are required for this purpose. The blue pin is not used when it comes to connectivity, which saves one PWM pin on the microcontroller. We were able to use only the red and green pins to display the 3 different status of the device. The red color for a reserved device, a yellow color to show an awaiting confirmation status, and finally green showing that the device is available. As shown on the board schematic, on the right, the red pin and the yellow pin are connected to resistors, which will connect to the main PCB board through jump wires. The main PCB board is 10 centimeters by 10 centimeters. The main components used are shown here. Connections to the keypad, LED PCBs, and ESP Wi-Fi module are done using female jumper pin headers to allow for easy removal. The push button, battery, and on and off switch are done using JST-PH 2-pin connectors. On this PCB, we have also included test points for debugging and programming purposes. We use through-hole capacitors and resistors for quicker assembling. However, the 2 voltage regulators are surface mounted since these were the regulators that met our requirements, making sure that the enable pin of the regulators go to the input pin. When designing the board, we made sure to avoid 90-degree angles on our traces and to increase the width of traces carrying supply voltage. We also created a ground plane on the bottom layer.
We have measured the current consumption during regular operation and have found it to be approximately 40 milliamps. When the ESP is transferring data to the Firebase database through Wi-Fi, current consumption increases to 450 milliamps, but this occurs for less than a millisecond. Based on our battery capacity, our device could run approximately 34.3 hours before requiring charge.
This is the first prototype for testing purposes of our project. We used an Arduino Uno board to program the Atmega 328P chip and debug it using the serial monitor. The rest of the components were laid out using a breadboard and jumper wires. For our power supply, we used an AC plug with a built-in AC-DC converter that provided 9 volts DC. Now we're going to move into the integration section.
In this part, the field to look up to is status. Status first starts as 1, which means the device is available and the light is green. Then the user will attempt to reserve a study spot, and the status will change to 2, which means the device is now in an awaiting confirmation with the light being yellow. The status field is now 2 and a 4-digit code has been randomly generated for verification purposes. The user will now go to the study spot location and use the keypad to enter the code. Once this verification is completed by the hardware device, the status is now changed to 3, and the light will now be red, which means the spot has been confirmed and reserved. Every time a new hardware device is manufactured, each will come with a unique ID number, which will be available to the admin in order to register that new device. This is important because we want to be able to recognize multiple devices in our database and interact with them from the mobile application. The hardware device will be checking for new information periodically, as well as changing the status based on the user input. And the software will be bringing the information back and forward to the user. In the backend of the application, Firebase will be in charge of handling the data in a real-time database. The admin, who can be an IT employee at the university, will set up the new device with the following fields: name, device ID, building name, floor, spot type, capacity, outlets, and whether there's a desktop available or not. All of these under the device ID number, which in this case is 0001. The fields, status, valid, and key code will be automatically set to their default values 1, 0, 0 accordingly. The hardware only has access to these 3 fields, and the admin is in charge of modifying the other fields for the device. This is now the mobile application.
For the front-end development section, there are 2 obvious programming languages that come to mind: iOS and Android applications. iOS requires the Swift programming language. Although Swift has some fast development times and performance under the hood, there are some drawbacks, which include cost, flexibility, and testing. For cost, it costs Apple developers $99 a year to publish an application into the App Store. Aside from high development costs, there is also limited flexibility when it comes to developing iOS applications, as they require Xcode, which can only be found in macOS products, which is resulting in limited more testing options as well. On the other hand, there are Android applications, which are written in Java, which is open source, meaning anyone with a computer can develop on it, which gives them for more extensive testing options as well. It is also cheaper to develop, requiring a one-time fee of $25 to publish to the Google Play Store. Unfortunately, this comes with slow development costs, as Android Studio, which is also used to develop, can be clunky and slow. So we found a third programming language that combines the best of iOS and Android, which is React Native, which is open source, is fast to develop on, and has moderate costs when it comes to development. This results in cheaper development costs and flexibility to develop on any platform. When it comes to data storage, there are 3 dominant database providers: Amazon's AWS, Microsoft's Azure, and Google's Firebase. Capturing the world's largest market share for cloud infrastructures, Amazon Web Services is the cheapest of the 3. They provide extensive documentation and beginner-friendly solutions. However, some drawbacks is that they're supported for large teams, which can be very costly in the long run if not managed right. And although they have a large variety of products to choose from, all of them have some slight of learning curve to them. For Microsoft Azure, they place a high emphasis on security and scalability, as they're geared mainly towards enterprise applications, which explains the high cost as well, which results in very expensive tiers and also requires a large oversight. Since our team is small, we don't need the high scalability that Microsoft Azure and Amazon AWS offer, so we went with Google Firebase, which has relatively cheap costs, no SQL programming, meaning no server-side programming, which cuts down drastically on development time, and simple implementation and integration with their APIs and simple authentication support, which means we can do simple user logins as an added bonus. The pros that Firebase provides during our research were mostly aligned with our project's goals, which explains why we chose Firebase for our database selection. For our use case diagram for our application, there are 2 main users: the user, which is a student, and an admin. The user will have 3 functions: login, search, and reserve through a regular login page. The user will log in through the application, and if they have not done so already, they will sign up via a registration page. When the user attempts to log in, a database will check if the user credentials are correct. If they are correct, the user is able to log in and see the status of the study spots. For search, the user will be able to see if the study spots are available, reserved, or pending reserved. For the reserve function, the user will be able to see if a study spot is available Then they're able to save their spot by reserving it, and if it's a pending state, they can cancel the reservation. For the admin, they'll have a special page where they have two functions: add and modify study spots. By being able to modify direct modifications to the database. For adding study spots, they can add a new entry to the database in order to add it by the device ID. And for modifying study spots, they can edit the database by deleting the device or modifying its properties within the database.
This is the UX UI for the student portal. On the Reserve a Study Spot screen on the left, the user will be presented with all devices available and non-available ones. They will be able to see the name of the device, name of the building, floor number, and icons as a preview before they make a selection. These icons represent if the study spot has outlets, a desktop computer, and if it's for an individual or for a group. Once they make a decision, they will be presented with a pop-up. In this pop-up, more information will be provided about the study spot. We can also see that the default value for key code is 0. This will be updated to the auto-generated code when the user presses the reserve button. The user also has the option to release the spot in case they have made a mistake or accidentally press on reserve. They will also have this release spot option when they want to leave their study spot. This is the UX UI for the admin portal. Ideally, the admin should be an IT professional from the university. On the left, we can see a list of devices already set up. These are devices that were previously added by the admin. Whenever they would like to add a new device, they can press on the Add button located at the bottom right of the screen. This action will take them to a different screen in which they're able to register a new device. They will have to add all the information about the device and have a device unique ID number available. This is an ID number provided to them when they purchase a new device. The admin is also able to press on each study spot and see its information and modify it whenever it's needed. For the entity relationship diagram, we have users as our main part of the application. These users will have a username, which is the email they sign up with, and a password of their choice. Admins and students are users of the application, which means they inherit all of the attributes of users. Many admins are able to set up many devices. Many students are able to reserve study spots, but only one study spot can be reserved per student. Students will have their student ID, full name, school email, phone number, and university name as part of their profile. Now, for the study spots, one or many study spots can have properties such as the ones you see on the right. The device ID is the one that identifies each study spot in this case.
Moving on to challenges. The following table shows the hardware challenges that we experienced during the course of this project, as well as the solutions that we devised to solve these problems.
There were a couple of challenges when it came to the software side of the project. The majority of issues with this project were with debug errors on this project, which is figuring out which was the right code for the job. The use of Google was a major help for the project. Emulation of this app was a bit tricky for us, as one of them have Windows and the other Mac OS, which proves the flexibility when it comes to developing in React Native. But when it came to testing, for the majority of the time, we used the Expo for testing in order to make sure our application was working correctly between devices. For integration between Firebase and React Native, we had to implement APIs, which involved reading the Firebase documentation.
Now we're going to look into the administrative side of the project.
The total cost can be displayed here, along with all of the components used to create one Study Spot Finder device. As you can see, the total was less than our budget of $100. For the distribution of work within our project, we assigned primary and secondary tasks to each member. In the following table, we can see each member's primary and secondary tasks. Thank you for listening.